I think it's a good thing that I have some, so that when you log into Zoom, you're in the right place. And so you see the, stuff that's going on today, and there's some weird music in the background just to kind of let you know that your sound is working and that you're in the right location. But I don't record all of that. So sometimes I forget to record when class actually starts. So hello and welcome. Tonight we'll cover chapter 15 material. There's also some chapter 14 material that I think I psyched myself out when I was going through chapter 14. I knew that we would spend some time this week, which was next time, talking about some of the aspects of heat moving from one location to another. And I think I decided to pull up short on the lecture, knowing that we would be covering some of this stuff this time. But I think I realized in hindsight that I left you a little bit short on the homework. So I'll talk a little bit about that stuff that we didn't cover last week. I wish I had. And then we'll talk about that. And then we'll talk about chapter 15. But then if you have any questions from the homework from chapter 14 before the quiz on that material, I am delighted to spend some time going over that. Tonight, we're talking about chapter 15. On Thursday, 2 days from now, I will hopefully field questions that you have from the practice exam. The practice exam for exam number 1 is in 2 parts. One part covers chapters 11 and 12. The other part is 13 through 15. So I strongly encourage you to look ahead to next week on our Canvas page and look at that material. I think I have Canvas open somewhere. I guess here it is. Let me move it up to here. And that's not it at all. And so this week is July 27th and 29th. Next week is exam number 1. Next Tuesday, 1 week from today, is exam number 1 on chapters 11 through 15 material. So when you scroll down, there's 2 versions of a practice exam. One is the practice exam on chapters 11 through 12 material, which is how I used to do it in the course. We would meet for like 2 weeks in the full semester and then have an exam, and then another 3 weeks and have a second exam. I've had some reasons for doing that. I've tried to kind of space out my exams from all of my colleagues, but eventually I fell into the idea that I just do 2 exams in the semester because that works pretty well for people. So in the 2 exam version, we will go chapters 11 through 15. There's a lot of material on the equation sheet. Some of that material is on tonight's quiz equation sheet, and I think all of it's on the equation sheet for next week's quiz. But I would love it if before Thursday night, you spent some time going through the practice exam and seeing what questions you have. If you can understand how to solve all of the questions, that's fabulous. But if there's any questions where you're like, I'm just not quite sure how to answer that one, on Thursday this week, I'm happy to answer any questions that you have. So if there's any questions that you do have on Thursday, please come ready to ask those questions, because I figure it's in your best interest to have a chance to ask those questions on the practice exam before you do a deep dive into studying for the exam. 1 week from today is exam 1, chapters 11 through 15. On Thursday, I'll go over any questions you have from the practice exam. I'll go over any questions you have from chapter 15 homework, and then you'll take the quiz on chapter 15 material. I think that's the best way to do it, that you will have done all of the homework on each of the chapters before the exam, had a chance to ask any questions on the homework before the exam, and had a quiz on each chapter's worth of material. The exam will not be identical to the practice exam. The exam will not just be a collection of questions from the quizzes, nor will it just be a collection of questions from the homeworks, but it is largely based on the homework, and the quizzes are largely based on the homework. So if you did the homework and understood it, if you did the quizzes and did really well, you are undoubtedly in very good shape for the exam. If you did not do as well as you wished you had, and there's something that's bugging you, gee, I thought I understood this, but then I didn't really, and I don't know what's wrong, feel free to ask those questions. One of the reasons that I do a quiz retake is that most people do really, or whatever, most people who didn't do well the first time they took the quiz do much better when they choose to retake the quiz, because they know what kind of questions they are, they know what material they have to look up, they figure it out, there's open book, open note, they can get it. But it's hard to do really well the first time through the quiz or the exam if you don't feel completely prepared. So I want you to feel completely prepared, and that's the objective here. Okay. So last time, we're launching into tonight's material. Last time we spent a little bit of time talking about this mechanical equivalent of heat. And I mentioned the fact that James Prescott Joule designed an experiment where masses fell down, and as they fell down, gravitational potential energy was converted into another form of energy. That other form of energy stirred a bucket of water. That water then increased in temperature, and there became an understanding that energy put into a substance like water would increase its temperature. And we figured something out about water in particular, that water required a certain amount of energy to increase its temperature, 1 kilogram of water, from 14.5 degrees Celsius to 15.5 degrees Celsius. And this, because water is this ubiquitous substance on Earth and is required for life, it seems to be a pretty important substance. So this was kind of the baseline that Joule used, and said, hey, you know what? Water requires a certain amount of energy, 4.186 joules, to increase its temperature 1 degree Celsius. Now it turns out that a lot of every different substance, every different pure material or material that's not pure, whatever kind of molecule it might be made up of different kinds of atoms, will have this feature that when you add energy to the material, its temperature will increase, but it's not necessarily totally unique, but pretty unique to the substance. And so this concept has been known as internal energy. So we know that heat flows from a high temperature object to a lower temperature object. But when something absorbs heat, its internal energy, the energy of the atoms and molecules, will increase. That's what we define as temperature. And if something releases heat or heat is removed from it somehow by putting it in contact with a colder temperature object, then it will lose internal energy and its temperature will decrease. But the amount of temperature increase or decrease is unique to the substance. So this is the equation that we have. Q, the heat that we add to a substance, equals M, the mass of the substance that we have, times C, lowercase c is standing for heat capacity or specific heat capacity. It was kind of born out of this false notion that it was kind of like juice in an orange or a grapefruit, and that the internal specific heat capacity of an object was, you know, the juice capacity of a grapefruit is bigger than the heat capacity of an orange, and there was some concept there, but it's way more complex than just the size of the object. So hang tight. Mass of the substance times the heat capacity of the substance, and it's unique to the element, atom, or molecule. And then delta T is the change in temperature that we see or observe or try to get to happen. So heat capacity is a physical property that relates how much of energy absorbed reflects changes in the temperature of a given substance. In terms of the units that we use for heat capacity, it'll be the energy required to change the temperature of 1 kilogram of the substance by 1 degree Celsius, or 1 kilogram, or 1 Kelvin, sorry. The units for heat capacity are joules per kilogram, degrees Kelvin. And because it's delta T, it doesn't matter whether it's Kelvin or Celsius. It's just same degree size. Metals tend to have low heat capacities. So when you put the pot on the stove, it doesn't take a lot of energy to get the pot to increase in temperature, and then it can have that energy go into whatever you're cooking. Non-metal substances tend to have higher heat capacities, and water, this ubiquitous substance on the surface of the earth, has a really high specific heat capacity. So we don't need to go through the whole history of things, but there is this equivalent of energy in the form of heat that increases the temperature of a substance. And we'll talk about that in a little more specific detail coming up. But wait, there's some weird stuff that happens. If I have cold ice, ice is a solid state of water. If I have cold ice and I add heat to it, I get warmer ice up until that ice is at 0 degrees Celsius. And then when I add more heat to the ice, the temperature does not change. That's weird. But I can notice that the solid ice starts turning into liquid water. the energy that I add to solid ice at 0 degrees Celsius induces a phase change. The solid ice turns into liquid water, and that all takes place at 0 degrees Celsius. While I have my ice water here, I will point out that I have ice and water existing together. And when all of that ice melts, this whole thing will still be at 0 degrees Celsius. And then when I add more heat, maybe unintentionally, but the room is warmer than 0 degrees Celsius, so it will happen. When I add more heat, the solid ice has all melted. It's all liquid water at 0 degrees Celsius. Then the liquid water will start to warm up. So when I add more and more heat to liquid water, it increases in temperature up until I reach 100 degrees Celsius. At 100 degrees Celsius, another phase change occurs. The water will remain at 100 degrees Celsius even as I add more and more heat, but it will change phase. Some of the water will jump into the gas phase and will turn into steam. And once all the water turns into steam and I add more heat, I can get superheated steam. So the phase changes from solid to liquid and from liquid to vapor are covered by this equation, Q equals ML. MLF, latent heat of fusion, when I turn a solid into a liquid or a liquid into a solid. And then again at 100 degrees Celsius for water to go from liquid into a gas or from gas into a liquid. Latent heat is a physical property that describes how much energy is required to transform the mass of a substance from one phase to another. And there's a couple of different versions of that. So just so you're clear, ice is cold. You probably knew that part. Ice is cold, and when I add heat to ice, then I'm going Q equals MC of ice delta T. The heat capacity of ice is about half that of water, 2090 joules per kilogram degrees C. And if I take cold ice, your freezer is at about negative 20 degrees Celsius. So I take the ice out of the freezer, it's at negative 20 degrees Celsius. And as I add heat to the ice, it increases in temperature, but doesn't start melting yet until it reaches 0 degrees Celsius, at which point Q equals MLF. At which point, the more heat I add at 0 degrees Celsius will stay at 0 degrees Celsius while the ice melts. At which point I will have liquid water at 0 degrees Celsius. Then we go Q equals MC water, delta T. And I will heat up my water to 100 degrees Celsius, at which point Q equals MLV. I'll have water at 100 degrees Celsius that is being converted into steam, and then I'll have hot steam, Q equals MC steam, delta T. And I can have superheated steam. You can get really bad burns from steam because steam can be hotter than 100 degrees Celsius. You can get a bad burn from boiling water, but that's only at 100 degrees Celsius. It's a steam that can be hotter than that and really burn you. So there's distinct levels here, right? So we start off with cold ice. We add heat until it gets to 0 degrees Celsius. And then at 0 degrees Celsius, when we add more heat, the solid ice, the solid water, turns into liquid water. And then we add more heat and we warm up our water, and then we turn it into steam once it's at 100 degrees Celsius. Clear, close, next. So water, you know, water has a melting point of 0 degrees Celsius. The latent heat of fusion for water, the heat that we have to add per kilogram in order to turn solid water into liquid water is 3.33 times 10 to the 5th joules per kilogram. Once we get up to 100 degrees Celsius, that liquid water starts to convert into gaseous steam. At 100 degrees Celsius, it takes 2.26 times 10 to the 6th, the order of magnitude higher energy to turn liquid water into gaseous steam. And then stuff that you probably kind of would infer, liquid nitrogen is very cold. So the temperature at which liquid nitrogen, solid nitrogen would turn into liquid nitrogen is very cold. And then not much warmer than that is the temperature at which liquid nitrogen turns into gaseous nitrogen. Likewise with metals, you probably would have the idea that most metals are in a solid state until they get very hot. So aluminum at 660 degrees will turn into molten liquid aluminum. And then if we care to keep going and we want to turn liquid aluminum into gaseous aluminum, we are going to be at ridiculously high temperatures in order to convert that into a gaseous state. So truly, I think you're in fine shape if you keep your attention focused on water. That's the ubiquitous substance on Earth. That's what we require for life to exist. And it covers things. So one of the homework questions that we can go over during question and answer time, if you have questions about it, is this question about, we have a container, a pot, an aluminum pot that contains water. And in order to increase the water to its boiling point of 100 degrees Celsius, we have to increase the temperature of the pot itself to 100 degrees Celsius. So the heat that it takes for the aluminum pot is going to be the mass of the aluminum pot times the heat capacity of aluminum times the change in temperature. So the mass of the aluminum was 0.75 kilograms, 0.75, times the heat capacity of aluminum, which is 900 joules per kilogram degrees C, times the change in temperature. The boiling point of water is 100. It started at 30, so 70 degrees Celsius. Likewise, we had to warm up the water. So the mass of water times the heat capacity of water times the change in temperature for the water. The water was 2.5 kilograms. Heat capacity of water is 4186, so much larger than the heat capacity of the aluminum, and the same change in temperature. And then the next step, we want to convert, MLF. We want to convert water into steam. 0.75 kilograms of water times the heat times the latent heat of vaporization of water, which I forget what it was, 2.26 times 10 to the 6th joules per kilogram, something like that. Some huge number for the amount of heat that we have to add to convert boiling water at 100 degrees Celsius into steam. And then we take all of that and divide it by 500. 500 joules per second. So joules divided by joules per second. The denominator of the denominator comes up to the numerator. The other things cancel and get how many seconds it took for this to happen. If that didn't all make sense, please ask questions during question and answer time. So what? Why do you feel cold when you step out of the shower soaking wet? Well, you're covered in water that is going from the liquid phase into the gaseous phase. Why? Because vapor pressure, because the layer of water on your body easily converts into the gas phase. So a lot of energy is being taken away from you. If you go to an amusement park in the dreadful days of summer, they don't want you to feel awful and overheated. So they provide these mist tents, and you walk through a mist tent and you get covered in these droplets of water, and then you step out and you feel so much cooler. It's not just because the water is cool and you're coming into some thermal equilibrium with cool water, but it's also because that water on your skin is being converted into the gas phase and taking heat away from your body as that happens, a huge amount. Now, one of the experiments that we would have done in person that we kind of fake with a video of me kind of talking you through the steps of doing calorimetry. And I know I asked a question at the very beginning, how many people had taken general chemistry before they signed up for this physics class, and a number of you had. In chemistry, there's an experiment called coffee cup calorimetry, where you take a substance, heat it up, put it into a coffee cup or a styrofoam cup, and measure the change in temperature as it reaches thermal equilibrium with the water that surrounds it. And you do kind of a quickie calculation where you ignore the heat capacity of the cup and just say, okay, how much heat got added to the water? What is the heat capacity of your substance? In physics, we might be a little more nitpicky, and we'll have a cup that is made out of a substance, aluminum, with a heat capacity that we know. So the water and the aluminum cup are at what? Room temperature. And then you add a hot substance into that water and cup system, and we can figure out the conservation of energy. All of the heat that came out of the substance, the block of metal put inside the system, gets absorbed by the water and the aluminum together. So that's the idea of our kind of calorimetry, where you figure the final temperature of the system means that heat is gained by the aluminum cup and the water, and that together must be the heat that is lost by the unknown substance, and then you can figure out the heat capacity of the unknown substance. Okay. That brings us to the end. So chapter 14, I wish I had taken you all the way to the end last time, but sadly I failed to do so. And there it was. Now, chapter 15, where we pick up on some of these same themes, we have some new material to cover. So chapter 15 brings us into this strange world. Imagine, if you will, that either NASA or some billionaire who's designing spacecraft announces that they can send human beings traveling at the speed of light to some other planet. And would you sign up to be someone to travel to another unknown planet that they think can support life? Would you be willing to sign up to travel at the speed of light? Well, there's some weird things that happen. As far as we know with physics right now, there's some weird things that happen as matter approaches the speed of light. Size changes. Time travels a little bit differently as you approach the speed of light. Traveling at light speed may be incompatible with physiology as we know it. You might just die if you traveled at the speed of light. I don't know. Maybe, maybe not. We don't know. We do not know the answer to that question. Could human physiology continue to work properly at near light speed? Well, in the 1800s, when scientific theory and scientific practice, what we typically refer to as engineering, kind of came to a place where steam locomotives were possible to be built. And so there was theory, and in that theory came the laws of thermodynamics. But then in practice, there became this stuff where you could shovel coal into a boiler, and by boiling water and converting it into steam, which had a lot of energy, you could harness the flow of that energy, the natural flow of that energy, from a high energy gaseous state into a lower energy liquid state and have it do work. And you could harness that work to push a huge, massive engine to move forward down a set of railroad tracks. And theoretically, in the 1800s, human beings might be able to travel at 40, 50, or even 60 miles per hour. But there was some debate, because could a human being travel that fast, or would they just die? Because the only human beings that had ever traveled any faster than the speed of the very fastest horses had died. Because if you fell off a cliff, you might have exceeded a speed of 40 or 50 miles per hour before you hit the ground, but then you died. So the thinking was maybe hitting the ground didn't kill you. Maybe there's something, just your brain could not process moving so fast. And so you just gave it up and died. So that literally was a debate taking place in the 1800s, whether you would build a locomotive engine and propel people down a track at 60 miles per hour and they would all be dead because nobody can travel that fast and survive the event. So turns out that human beings can survive going faster than that. But that technology developed in the 1800s, filled with concern and maybe some dread and some protests, is the technology that up until a few years ago fueled the Salem power plant. The Salem power plant a few years ago that gave us all our electricity here in Salem, Massachusetts, ships filled with coal would pull up to the power plant and dump the coal, and they'd convey the coal into a boiler furnace that would boil water, and that boiling water would turn a steam turbine, and that would generate the electricity that we have here in Salem, Massachusetts. More recently, they converted that from coal to natural gas, and so there's pipelines that bring natural gas into the power plant, and they burn that natural gas, and that boils the water that turns the steam turbines that creates the electricity in Salem, Massachusetts. Higher technology might be nuclear. Nuclear energy has a controlled nuclear reaction that is boiling the water that turns the steam turbines that generate electricity. We really haven't, for the most part, for our energy production in the world, haven't gone far beyond what we're going to talk about tonight, heat engines, taking a high temperature region and a low temperature region and harnessing the fact that the natural flow of heat goes from high temperature to low temperature and getting that to do some work for us. That is a heat engine. There are other ways of producing electricity, solar and wind. Those are not, probably not even as efficient as heat engines, but at least they're not as bad for releasing pollutants into the atmosphere. But all of this stuff is pretty inefficient. It's too bad. So hold on for a moment. We mentioned briefly that when you add energy to a gas, it increases in temperature. That was one of the things that we kind of came up with when we talked about the ideal gas law, was this internal energy of an ideal gas. 3/2 NKT was the equation that we ultimately came up with. But that's internal energy that's good enough for right now. Another aspect that we're going to talk about is work. Now work from physics 1 was if you lifted something up. Hoorah, I lift something up. And when you lift something up, work equals mgh. It's a force through some distance, and the force is the weight of the object, and the distance is the height that you lifted up. There's another thing that we've been talking about that's called heat. It's related to the temperature, but not directly so. 3/2 NKT. But heat and temperature are related, and heat can be stored in an object by heat capacity that we just talked about, and heat can have some other roles that we will talk about shortly. Just trying to find my place here. Okay. Oh, sorry. So first of all, with heat and work, we're going to have some definitions. If a system gains heat, then heat is positive. If a system loses heat, heat is negative. If the system does work done by the system, that's positive work. If work is done on the system, that would be negative work. So, very simple scenario. We have a gas trapped inside a vessel. It has some initial temperature, which means that gas has some initial internal energy. If I add heat to that gas, the internal energy will increase, the temperature will increase, and so the final internal energy equals whatever the initial internal energy was plus the amount of heat that I added. It's all in joules. So joules of internal energy, joules of heat, and then a final joules of internal energy. Likewise, I have this hot gas sitting inside a vessel with a movable piston. It has so much heat in there that it has a lot of pressure. That pressure exerts a force. That force acts over a distance, and it lifts up this gold brick some distance. So it did work. The system did work on the gold brick. And the final internal energy, this was really hot when it started, but then when it lifted it up, it lost that energy. So the final internal energy equals whatever the initial internal energy was minus the work that it did lifting it up. So ultimately we get to this thing that we call the first law of thermodynamics. The first law of thermodynamics is that heat minus work equals the change in internal energy. This is written in a number of different ways, but delta U equals Q minus W is probably the most common way. Heat is in joules, work is in joules, internal energy is in joules. So it all works out with units, but that's the idea. So if we were meeting in person, and this were, I don't know, 5 years ago, I used to walk into the lecture hall with a cart, and that cart had a projector on it. And I would walk over to the projector and tilt it up at an angle, because we've been talking about work as the change in gravitational potential energy, and having someone run across a level beach does not convey a change in gravitational potential energy. So I'd pretend that this person was running uphill on a beach, which makes no sense whatsoever. But if you can give me that much, then I would say that this person running on the beach is increasing their gravitational potential energy. So they're doing work. They're the system. They're doing work. They are emitting heat into the atmosphere. When you run on a uphill beach, you are sweating, right? So this person is losing heat to the atmosphere, and so their internal energy is decreasing. We would say they're burning calories. And if they don't want to burn too many calories, maybe they'll sit down after this exercise event and eat a bagel and then gain their energy back. Okay. One kind of harsh reality with thermodynamics is that nothing is ideal. So an ideal situation would be, I place the gold brick on top of the piston goes down. Work is being done on the system. The system is the gas trapped inside here. I push down, I'm squishing it, I'm increasing the pressure, I'm increasing the internal energy. If it's going to stay at the same temperature, it has to lose heat from inside to outside. But then I could completely turn it around and it could gain the heat back at the gold brick would go back to its original location. That would be ideal. Unfortunately, life is not ideal. The piston and the walls of the container probably have some friction, so energy is lost somehow. Nothing ever returns to exactly the same place it was before. So we have ideal, which we'll talk about, but then we have reality, which is, less than ideal. Okay, we have a gas under pressure inside a container with a piston that has it at a certain volume. And then as the piston moves out, the volume increases. Again, like maybe tilt your heads to the side. This would be lifting the piston up, so it's doing work. Work equals P delta V, pressure times the change in volume. So when we depict that on a graph, it would be something like this, that the work is the pressure, this is constant pressure, times the change in volume. And when I multiply those two numbers together with the right units, I would come up with work in joules. It's the area under the curve. I could have that be a little more weird and have a triangle on top of a square, and I could add up both of those areas, or I could have all sorts of weird stuff, but just kind of hang on to that for a second. Add heat to a system at constant volume, and I'm going to increase the pressure. I'm not sure why I said that right there. Hold up. I'm coming up to some equations. I think I just have these in the wrong order, but it's fine. These equations will appear on your equation sheet. There's 4 different circumstances that we might have with a gas trapped inside a vessel. One of those situations is constant pressure. If I add heat to the gas and I allow it to equilibrate to what? Atmospheric pressure, constant pressure. If I add heat, I've added internal energy, and the volume will increase, and I will have done work on a system. So work equals P delta V, or if I'm interested in the heat flow, I could say Q equals delta U plus P delta V. If I instead restrict it so that it can't change in volume, we've said that work equals mgh, which means that work equals pressure times the change in volume. But if the volume doesn't change, then there's no work. There can be no work because the piston didn't rise any higher because the volume didn't change. So work equals 0, which means that any heat that I added all went into internal energy. I've increased the temperature of the gas. Another case is isothermal. Isothermal is when the temperature doesn't change. If the temperature doesn't change, because internal energy equals 3/2 NKT, if the temperature doesn't change, then the internal energy doesn't change, which means that according to the first law of thermodynamics, all of the work went into heat, or all of the heat went into work. The other case is a little bit weird. It's adiabatic. That's if there's no heat flow. If there's no heat flow, then since the first law of thermodynamics would say that work is related to heat and the change in internal energy, then any work that is done by the system will result in a decrease in internal energy of the gas. Ooh. We do not need to worry about heat capacity at different situations. So here's the deal with heat engines. Heat engines have a high temperature reservoir. We extract heat from that high temperature reservoir. We take advantage of the fact that heat naturally wants to flow from a region of high temperature to a region of low temperature. And as the heat flows from a region of high temperature to low temperature, we have it do some work for us and then let the waste heat dump into the cold temperature reservoir. In terms of like a steam locomotive engine, we shovel the coal into the boiler. The fire turns liquid water into gaseous steam. Gaseous steam is at a high energy, a high pressure. It pushes the piston out. The piston is attached to a set of gears and various other things that make the steam engine work. The piston goes out. As the steam pushes the piston out, it loses energy. It starts to condense, but then we expose it to a region of even colder temperature, and the steam condenses into liquid water. We then pump that liquid water back up into the boiler, turn it into steam again, and back through the process we go. So high temperature reservoir, low temperature reservoir, the amount of heat, QH, that we extract from the high temperature reservoir, the amount of heat, QC, that we dump into the cold temperature reservoir, and we extract some heat. The efficiency of this heat engine is actually dreadfully low. The amount of work that we get done versus the amount of heat that we've extracted from the high temperature reservoir might ideally be 24%. In reality, will be much lower than that. That's how a heat engine works, high temperature to low temperature. You can make a heat engine work in reverse. You can extract heat from a cold temperature region and dump it into a high temperature region if you turn it around and do work on the system. So I have a refrigerator in my kitchen here. I am extracting heat from the cold temperature region, the inside. I have my refrigerator plugged into the wall. There's a motor that is operating a pump that is taking a gas and condensing it and then allowing it to expand. The expanding gas has a cooling process. It cools off the inside of my refrigerator, but then the waste heat is both the heat inside my refrigerator being dumped into the kitchen at large, as well as the energy from the motor, the waste heat from the motor running, dumping into the kitchen. If on a very hot day, you just stand with your refrigerator door open, you might feel nice and cool on your face, but ultimately in the fullness of time, you are heating up your kitchen. Likewise, if you have an air conditioner, if you ever notice a window unit air conditioner is mounted into a window with the waste heat being dumped outside into the rest of your neighborhood. The cold temperature reservoir is the inside of the room that you're cooling down. You're doing work and you're dumping both the work and the heat from inside the room into the outside. If you just decide to take a window unit air conditioner and plunk it on your kitchen table and plug it in, the net result will be heating up the room, not cooling it off. This is still tied in to the first or second law of thermodynamics. The second law of thermodynamics is that when objects of different temperatures are brought into thermal contact such that heat can flow in between them, the spontaneous flow of heat is from the high temperature object to the low temperature object. That's the natural flow. You can input a whole bunch of energy and get it to go the other way, air conditioners and refrigerators, but that's not spontaneous. Anytime you have a high temperature region and the low temperature region brought into thermal contact, the natural flow, the thing that will just happen, is from high temperature to low temperature, and you can harness that flow of heat in order to do work. Part of the second law of thermodynamics includes that this happens and it increases entropy. My sister-in-law was very bummed out when she got her PhD in bioanalytical chemistry, and she thought she was getting her degree in science, And then she got handed her diploma and it said Doctor of Philosophy. But we all know that PhD stands for Doctor of Philosophy. The philosophical thing, kind of the weird thought experiment that we have here, is that entropy, an outpouring of the second law of thermodynamics, is that things tend to get more messy, tend to get more disordered. Solid ice sitting on my kitchen table will naturally absorb heat from the room around it and turn into liquid water. Liquid water, a big puddle mess on my table, is a lot more disordered than that solid ice cube. If that liquid water continues to absorb heat from the environment, some of those water molecules will get so energetic they jump into the gas phase. And just because air is moving around in the room, those gas phase molecules will move off. And that solid ice cube, in a matter of hours, maybe a few hours, will turn into just this vapor that's not visible at all, but is added to the, water content, the humidity in the room around me. This is entropy. It is that everything tends toward more disorder. And the equation for that, delta S equals Q over T, it's the amount of heat that flows as something moves from one state to another at the temperature at which it happens, and it's joules per Kelvin. Entropy is not conserved. Entropy is always increasing. Everything that we're aware of tends toward more and more disorder, or at least toward a more and more equilibrium temperature. And that, the third law of thermodynamics that I don't seem to have a slide about, let me just tell you, the third law of thermodynamics is that there's this thing that we call absolute zero, at which all motion stops. But to the best of our knowledge, absolute zero, where all motion stops, is not achievable in any finite number of steps. If you want to cool down your liquid water and turn it into solid ice, you put it into contact with something that's colder than 0 degrees Celsius. If you want to turn that solid ice into very cold solid ice, you put it into contact with something that's colder than that, and so on and so forth. But there's nothing colder than absolute zero, such that you can't get to absolute zero. Okay. So let me tell you, I have a quiz for you this very evening that is based on chapter 14 material. I would be delighted to answer any questions you have on chapter 14. You can ask those by unmuting yourself and asking, or by typing them into chat. You can do private chat if you don't want to be associated with the question for some reason. But any questions you have on chapter 14, I am delighted to answer. And if you don't have questions on chapter 14, I would encourage you on our main Canvas page to scroll down a little bit to the chapter 14 quiz. I'll preview it. Here's the set of equations. Obviously, some of these are related to chapter 15, but some of these are related to chapter 14. Some of these are multiple choice. Some of these are numerical answers, but I believe all of the equations that you need to answer these questions are provided, and there's a space for you to show your work or upload your work, or you can email me your work so that I can give you partial credit. So I will leave the equations here for you to look at while you take the quiz, unless there's any questions. And seeing none, I will go ahead and stop the recording.